The energy transition demands materials that are cleaner, stronger, and smarter. Materials that can store energy more efficiently, catalyze reactions for a hydrogen-based economy, and reduce our environmental footprint. But to design these materials, scientists need to see what happens at the atomic scale, to observe matter as it transforms, reacts, and evolves in real time. InCAEM, the In-Situ Correlative Facility for Advanced Energy Materials, is a new infrastructure located at the ALBA Synchrotron and open to the scientific community, where scientists can connect advanced electron microscopy, scanning probe techniques, and synchrotron light to explore materials in action. The project has been funded through the Planes Complementarios program within the Advanced Materials Project in Catalonia, supported by the Ministry of Science, Innovation and Universities, the Generalitat de Catalunya, and the NextGeneration EU funds. Developed through the joint effort of the Catalan Institute of Nanoscience and Nanotechnology, the Institute of Materials Science of Barcelona, the Port d'Informació Científica, and the ALBA Synchrotron, InCAEM represents a shared commitment to advancing materials science for the energy transition. Since October 2022, the project has incorporated different members to their teams to design, acquire, and commission the new equipment and build the infrastructure to have a new set of tools ready for the scientific community.
InCAEM is a new research infrastructure dedicated to developing, understanding, creating advanced materials for energy. It provides an unprecedented platform to science in academy and industry for tackling complex problems in this field with correlative methods. And this field is essential for the sustainability of our world.
At the core of InCAEM lies a state-of-the-art scanning transmission electron microscope that is capable of visualizing materials with sub-angstrom precision.
This is the STM platform, in which we have a very unique microscope which has the capability to exchange voltages from 30 to 300 kiloelectron volts with a high versatility and stability, and allows to study materials for energy, for example, in operando and in situ conditions. And we have sample holders that can be used both in the TM and in the synchrotron beamlines, in which we can do correlative analysis, for example, analyzing the oxidation and coordination state of the, for example, catalytic sites.
An advanced scanning probe microscopy platform is also available to offer and correlate information at the nanometer level about the structure and physical properties of materials, enabling in situ and operando experiments that reveal how materials behave under real working conditions.
We are in one of the laboratories of the scanning probe microscopy platform. Here, the microscope behind me is operating under ultra-high vacuum conditions. Beyond that, through the window, we have the other laboratory with two atomic force microscopes, one inside a glove box, the other one inside acoustic enclosure. With both AFMs, atomic force microscopes, we are able to operate under inner gas environments as well as in liquid or electrolyte solutions, providing valuable opportunities for research in electrochemistry, catalysis, and electronics.
The SPM platform has two of these photon SPMs that share some common features with the other microscopes, which is the fact that it has a very narrow probe that is positioned very close to the surface of the material in order to feel the interactions locally and therefore map not only the structure but also magnetic, electronic, or even chemical properties. So these photon SPMs are adding the capabilities by putting light in and out of this junction, and therefore trying to see how light is absorbed and emitted from these materials also at the nanometer scale. So this is relevant for applications such as photocatalysis or optoelectronics.
By combining these techniques with X-rays from the ALBA synchrotron, chemical, structural, and magnetic insight of materials is explored, promoting true multimodal and multi-length scale characterization.
Within InCAEM, we want to combine electron microscopy and scanning probe microscopy, very powerful techniques that allow us to see things as small as atoms, with the full power of X-rays. That is, to combine these microscopies with the X-ray beamlines at ALBA, in order to understand complex problems by looking at a sample or a process from different points of view, combining structural information at different length scales with chemical, electronic, and magnetic information. This is the way to really understand the whole process.
Beyond the instruments, InCAEM is also a digital infrastructure with robust computing systems and automated data analysis pipelines to accelerate discovery and innovation.
At ALBA and PIC, we provide offline and online data analysis platform. And at PIC, we contribute also with our experience in artificial intelligence to help accelerate research in material science.
From catalysts for clean energy to materials for environmental applications, InCAEM helps us understand how atoms move, react, and transform, paving the way for new technologies that power a sustainable world. A pioneering platform born from collaboration and the shared goal of building a greener, more sustainable future for Europe.